Chief Editor of the journal Nature Nanotechnology, and I'd like to welcome you all here for this celebration of this anniversary of graphene. It was 15 years ago that a group of scientists in Manchester, led by Serguei and Konstantin Novoselov, published this paper on an electronic device made with very thin layers of graphite. It was a paper. There's millions of papers published every year, except this wasn't just a paper. It was the beginning of the research field of graphene and 2D materials, a field that was going to become very prolific. And soon, graphene became the material superlatives. The thinnest is only 1 atom thick, so it's actually two-dimensional. The strongest, the most conductive, and so on. In the 15 years that passed from there, a huge number of papers were published on the fundamental properties, but also on the potential for applications. And, graphene and two-dimensional materials is the core of nanotechnology. So as a journal that publishes nanotechnology, we really felt that we wanted to celebrate this anniversary. And what better way to do that? We're one of the protagonists of that discovery. So from the original idea and the vision of my colleague, Olga Bubnova, and with the help of the sponsorship from the Schaffhausen Institute of Technology, we have come to this event that I hope you will all enjoy. And if you do enjoy, please feel free to tweet about it, go on social media, use the hashtag GrapheneTurns15. If you don't enjoy, just keep it for yourself. Don't say that to anybody. But in about 20, 25 minutes, Professor Novoselov will give us his view of the field. But before that, we have two other speakers. The first one is a scientist and a science publisher, has a huge expertise in science publishing. She's had several roles, and she's a real enthusiast of the future of science publication. And since about a year and a bit, she's the editor-in-chief of Nature. So please help me to welcome Magdalena on stage.
So good evening, everyone. It's really an enormous pleasure to be here. And I think Fabio didn't say that as well as being an enthusiast of science, I'm actually a geneticist. So I will read some notes because I think it's quite rare that geneticists open a public lecture on graphene. But please don't take it that geneticists always read when they introduce lectures. So I will start with a quote. Amid a wealth of remarkable carbon-based materials, no other stands out quite like graphene. These are the opening words of this month's editorial in this month's issue of Nature Nanotechnology. And of course, we are here today to celebrate a 15th birthday of graphene, this very special teenager. For most of us, this journey started 15 years ago when a report was published demonstrating that a stable single sheet of carbon could be isolated. This experimental announcement of graphene marked the rise of 2D materials of the whole era and was, of course, the subject of a Nobel Prize only 6 years later. Today, we know that graphene has one-of-a-kind mechanical and electronic properties. Indeed, there has been remarkable progress in graphene research quicker than any other material. So I said that the journey started 15 years ago. But alas, it did not start in the pages of Nature. And that's not because the authors didn't choose to submit to us. If ever there was an argument in favor of editors overruling reviewers, here's one example of it. Fortunately for us at Nature, the authors, Serguei and Konstantin Novoselov, who is here in the audience, of course, were undeterred. And just a year later, in 2005, Nature published their paper which describes graphene as a benchtop model for quantum measurements. So allow me to quote a rather elegant ending to the abstract of their paper. This two-dimensional system is not only interesting in itself, but also allows access to the subtle and rich physics of quantum electrodynamics in a benchtop experiment. To date, Nature titles have published more than 50 papers authored by Serguei and Konstantin Novoselov. More broadly, the Nature research portfolio, we have published more than 1,000 graphene-related papers. I will mention just a small handful here, and bear in mind that the selection was made by a geneticist. So for example, in 2006, there was a report of a convenient route to fabricate a variety of graphene polymer composites, thereby improving the performance of these composites. 2 years later, in 2008, Nature Nanotechnology published a paper describing a high-yield liquid phase exfoliation method, which turned out to be an extremely versatile technique that can now be used to produce a wide range of nanosheets. A year later, in 2009, that brought a breakthrough in photonics for graphene. Nature Nanotechnology again published work revealing the great potential of graphene for ultra-fast light detection applications in a very broad wavelength range. A year after that, again, Nature Nanotechnology carried a paper in which the authors demonstrated the growth of graphene films up to 30 inches wide by their transfer onto insulating substrates, followed by the transfer onto insulated substrates. A key step, of course, for actual use of graphene in commercial devices. And more recently, just last year, a paper in Nature described an observation of unconventional superconductivity in graphene bilayers. The work showed the relative twist, how the relative twist angle between the 2D crystalline lattices can have a dramatic effect on the electronic properties of materials. This paper essentially gave rise to a new field, which has been dubbed twistronics. So back in 2007, Ondřej Geim and Konstantin Novoselov described graphene as a rising star on the horizon of material science and condensed matter physics. That year, they published an influential review in which they made predictions about the future directions and economic innovation aspects of possible applications of graphene in composite materials, batteries, quantum computing, and electronics. But we all know that the future is notoriously hard to predict. While graphene has yielded some phenomenal insights into fundamental physics, we're still waiting for the comparatively impressive application of graphene. Hence, for example, the large community efforts such as the flagship. Whenever those applicable breakthroughs come through, we certainly hope that we at Nature Research Journals, we can report on them in our pages. So it really is an enormous pleasure to be associated with this public lecture, and thank you again for the opportunity to introduce it.
Okay, so science progress proceeds in two ways, really. One is the understanding of the fundamentals of nature. One is the potential technological advances. In reality, even if we don't always see that, they go hand in hand. And graphene is a very good example of this. In fact, Magdalena just alluded to it. There's a continuous discoveries of the fundamental, new exciting fundamental properties, but also a strive to get devices out of graphene. But there's something even more about it. One thing that I've always liked since I actually started my work as an editor is the fact that graphene, it seems to be a meeting point for scientists with very different backgrounds. Initially started with condensed matter physicists and organic electronic persons, but then also chemists and even biomedical engineers now work together to get something out of that material. So our next speaker is in fact a real enthusiast about the collaboration and synergy between people from different backgrounds to achieve the same goal. He comes from the same institute as Konstantin Novoselov. He comes from the Moscow Institute of Physics and Technology, except instead of becoming a scientist, he decided to invest in talent. So he's become an entrepreneur. He's been an entrepreneur for many years. And among other things, he's the CEO of Acronis and the founder and chairman of the board of the Schaffhausen Institute of Technology. So please welcome Serguei Beloussov.
I have a very long presentation. I only have 15 minutes, not to take the time from Kostya. So this is very quickly, who am I? I am currently running Acronis. Acronis is a mid-sized software company. We are growing very rapidly to $1 billion in revenue in 2022. We serve almost every large business, a very large number of small businesses, very large number of consumers. We are headquartered in Schaffhausen. That's where Schaffhausen comes into play. And we also have a second headquarters in Singapore. We build cyber protection software to make sure that you are safe, authentic, private, accessible, and secure with all of your data applications and systems. And we're officially a unicorn. That's just to say that we have enough capital to fund what we want to do with Schaffhausen Institute of Technology. So the universe is a computer. This is a well-known fact right now. Many books are written about it. Everything which happens in the universe effectively is a quantum or some other form of computation. And as a result of it, we can use computers to do many things and to predict the universe for our benefits. And we do it all the time. There is no doubt that computers have changed the way we live. This is, for example, the prediction of Hurricane Dorian. You can use powerful computers to predict its path. And today, most of computers we use are digital computers. In fact, the concept of computers and computer science was to some extent invented in this country by Alan Turing. And still today, we use a very basic architecture everywhere, which is called von Neumann architecture: input, central processing unit, storage, output. So that's an architecture. We rely on this very famous Moore law, which is not really a law of physics, but rather an observation about the fact that computers double its power every 1.5 years. And the fact of the matter is that Less law is coming to an end. It has been active for 60 years, and this wonderful organization, ITRS, saying that it's going to stop in 2021. But even in case it wouldn't, there are two physical limits for digital computers. One of them is a Bremen limit, another one is Margolis limit. This is like 60 years, 75 years. Not very long. Maybe some of us will not live that long, but in 60 or 75 years, we're not going to get faster computers. And this guy, Scott Aronson, and many, many people estimate that we reach the limit of this architecture in 25 years. Well, what are the problems with computers? There are 3 problems, which are very, very sad. One of them is performance and bandwidth is limited. We cannot do too much. Power consumption is unlimited. We don't have unlimited amount of power. We just have sun in our ecosystem, in our solar system, and that's not going to be enough at some point. And also, the computers could become very large because there is a size of the transistor problems. Yet there are very simple mathematical problems. This is Cauchy inequality, looks a bit theoretical. How many of you here knows Cauchy inequality? Huh? There is scientists here. Question must know. Anyways, there are 2 other problems which are very conventional. One is factorization, very basic thing, very large number. You can multiply 2 large numbers, but to find the factors is impossible. That's the source of all encryption techniques today. And many body problems in physics, you can actually create a formula for how matter will behave, but you cannot actually calculate it. And so it's useless. You have to guess, and you have to combine different materials. And it would be nice to solve them, but you cannot solve them on conventional computers. As a result of it, many of these problems, which are real problems, which can be solved with better technology, war and violence, why should people kill each other? Environment and global warming. Clearly, environment is a problem. Global warming, there is debate, but it sounds like it's a problem too. Spreading of poverty. We get 7 billion people. There's more and more very poor people which do not participate in the society. Disease and aging. That's undoubtedly a problem. Nobody wants to die. We are all very sick here. In this room, all of us are sick with the fact that we're going to age and die. Well, it's not necessary. We can live longer, but we really don't know how to solve it yet. We can possibly solve it with better computers. And of course, space and universe challenges. In order for us to travel to other planets, there is many, many other things to solve. And so, for example, when I say about disease and aging to a journalist here, they say like, well, is it really good to solve it? Because then maybe it will be too many humans on Earth. And apparently, I think it's good, let it be more humans. I don't really want anybody to die. But otherwise, if you solve the second one, there is no problem, right? And so this is a computer of 1912. And what computers do is they compute, they store, and they send the data around, very basic devices. And today we rely on this 3 architectures: CPU, which is in every PC, every server, every mobile phone; GPU, which is now getting more popular for certain types of calculations like machine learning, like computer vision, highly parallel; and TPU, which is a new way of computing by Google, which is designed for machine learning, right? All of them are effectively digital computing, not very good for example, imitating human brains. This is neuromorphic computers. This is very new Intel Loihi chip, just released, 128 cores. This is just sort of being released, very large chip with 1.2 trillion transistors on a single chip, which is significantly more than in the largest CPU designed for machine learning. This is memory star machine. This is a new types of machines, still digital machines, but specialized for solving, for example, machine learning problems. Then you have photonic computers. Both photonic and new generation neuromorphic computers are coming in to solve power problem, especially in the case of deep learning and machine learning. You can do a lot of things, but it's too much energy. Then you have quantum computers. I don't have time to overview it, but there is significant progress in this area with superconducting qubits. There is many other design, IonQ by a friend of ours, Chris Monroe in Maryland, and Honeywell. Cold atoms by Misha Lukin, who is my classmate in Harvard. Photonic computers, there is real progress with this computer. So quantum computers, which 10 years ago were sort of, if you ask scientists, maybe 10, maybe 20, maybe 50 years from now, maybe never. I think next year we have quantum computers which solve real problems. This year there is already result that they are better than normal for some things. This is sort of other example, a relativistic computer, black hole computer. So black hole is a computer apparently. Very, very fast one. It can calculate things in 10 in the power of 35 if we can figure out what to ask it to calculate, cannot store a lot of memory. Advanced materials computer, Kostya will talk about it. There are some things which are very difficult to emulate on difficult computers. For example, how we grow our bodies. Noise-free analog computers, Claytronics computers, very different types of computers. It's interesting, but for some problems, these very weird computers, like analogous computers, are still better than any digital. Now, you have this wonderful computer, which is in the brain of every person in this room, which is a human brain. It's in your head, right? It's the most interesting object in the universe. It has 100 billion neurons, 100 trillion connections, 10 watt of power consumption, very power efficient, much more power efficient than any computer. And it's extremely parallel, and apparently it's creative, so it can serve Gödel theorem. It's completely unclear how to solve Gödel theorem on any Turing machine. So it's maybe that human brain computer is more sophisticated than any digital computer, and it's very, very good, right? And so then there are these problems which require new generation computers already today, robot sensors and actuators. This whole architecture of a robot, which is a machine where you have a sensor, it senses something, then this information is sent to central processing unit, then it's processed and it's sent back, and it does something. There's high latency, there's a lot of power, it's slow, it doesn't work. So you think about we master nature, we have planes, and the planes fly any way they want and very fast, much better than birds. In reality, if you look at birds flying in this room, they will be flying very freely. They can stop, they can start, they can go left, they can go right. We cannot actually have any flying machine. You know, the F-22 Raptor, an amazing 5th generation plane, when it does all these wonderful aerobatics tricks, it's actually, in comparison to almost any bird, it's completely awkward, right? So you need new computers for that. Telecommunication, today, internet is very slow. Many of us see it, even in the center of London. The reason for that is because internet is not fully photonic, and there is a lot of switches in the middle, which are semiconductor switches, which convert photons into electrons and do something with them, then convert it back, and there is a lot of latency because of that. Data storage is not very good. You need specialized data storage. Today, storage is not very long term. Today, everything we do is recorded in the computers, but it cannot be stored for 1,000 years. So if we want to store something for 1,000 years, we might likely need to print it and keep it somewhere in hardware form. And of course, we have a lot of need for computers to help sick people and to solve problems which happen with our brains, right? And so this is sort of a fantasy machine which I constructed. There is an open interconnect called Gen Z, and you can combine all of it. So GPU, CPU, TPU, that's already Google Cloud today. Memories or Amazon Cloud, photonics, quantum computers, very soon, and some other computers combined with human brains, you can create this sort of Earth-wide computer, which can solve a lot of problems. Now, in order to make this computer, you need several things. First of all, you need new materials. And this is an example of new materials, which at least two of them resulted in Nobel Prize, right? So The first material, monocrystal silicon, is required for all of the CPUs and TPUs and GPUs. In order to have such a small transistors, you need to have very special silicon. It does not exist in nature. The second one is needed for lithium-ion batteries. Again, just got a Nobel Prize very conveniently for the speech in 2019. This third one is also another special material, very special glass for optical fibers. Without optical fibers, we cannot have proper internet. Even today, if I want to send 1 petabyte of data from here to New York, the best way is to copy it on something, put it in the bag, and bring it to New York manually. Over optics, it's not going to be very fast. Neo-medium and the other two are both for our hard disks. So this is the new materials needed to build new generation computers. To build existing computers, there is a lot of advanced materials for the future computers. Then, of course, you need new hardware. So it's good for physicists. They built a quantum computer, so it can theoretically do something. But for this quantum computer to be useful for us, we need to control it, we need to operate it, we need to insert the data, output the data. There is a lot of things which needs to be done, and this hardware does not exist. There is a need for the software to design those computers. And a lot of those computers cannot be designed with conventional software. The software is not written, so there is a need for software engineers, very different type of species. They are not physicists, right? There is a need for operating systems for those computers, which are not the same operating systems. Operating system which we run on this device today, the iOS device, this is iPhone 11, with 3 cameras. I'm waiting for the one with 8. And those, in any case, this is the same operating system which was designed 50 years ago. It's a modification. It kind of has the same things. You need maybe completely different system, for example, for advanced materials-based computers. Then you need to actually put into software the algorithms for these computers, because ultimately we live in a physical world. So, for example, to communicate with quantum computers, it's unlikely that we will be able to have a quantum interface to a quantum computer. Our interface is digital. And so we need to take our digital problem and encode it in such a way that it can be put inside the quantum computer. And then we can read the output and produce something digital for us to understand. So for that, we decided to build a new interdisciplinary university. I don't have much time to talk about it, so I'm just going to say that that's going to focus on science. It's going to focus on master, PhD, and postdoc. It will have an undergrad program. It is focused on the 3 fields, computers, physics, and business, combined together with a single goal to build a new generation computers. The headquarters of this university is going to be in Schaffhausen, Switzerland, which is an amazing place. It will be self-sustainable. It will have enough funding. It will have, hopefully, better funding than any of the science group in any of the universities in this wonderful country, including such a wealthy universities like Cambridge and Oxford and Manchester University and so on. But it will not have a lot of scientists. It will combine science, technology, and education in one place. And this is some of the KPIs for this university. This is specific focus area, cybersecurity, information integrity, very important. Everybody understand this. Artificial intelligence, machine learning, software engineering, and robotics, all of this is needed to build new generation machines. Quantum technology and advanced materials. And advanced materials is the only reason we're here. Kosti is not just a member of our strategic advisory board, but he is a chairman of strategic advisory board. And then we want to apply this to business, digital health, new generation business management, digital law, digital sport, digital learning and education. Very important thing is to change how we learn. We do learn the same way as we were learning 1,000 years ago. That's completely weird, right? So we consume information differently, but we learn in the same way. And then, of course, AI in arts as well. This is Schaffhausen. This is basically the Rhine Falls, which is the largest waterfall in Europe. We may be not the largest university in Europe, and we may be not the best university in Europe just yet, even though that's our ambitious goal. But we definitely have the most beautiful site for the university. You see here, this is a Rhine Falls. So from the university, you can see the Rhine Falls. It's much nicer. I've been to Manchester, and I've been to Cambridge and Oxford, and the view is amazing, right? And so this is why Schaffhausen, it's next to the Zurich airport, 30 minutes. Anybody been to Schaffhausen in this room? Right, so few people have been. I mean, our team was. It's next to German border, 5 minutes, so you can live in Germany if you want. Anybody speaks German here? Well, come on, you are some people who speak German, right? And it's an old city, 1,100 years old, very important, of course, for the university. And it's very small, so it's not super expensive. There is good industry there. It's really very nice place for the university. And it's really very nice place for a scientist or postdoc, especially postdoc and PhD student, to have his studies and to even have a family and to further find a job if he doesn't want to move somewhere. So that's it, what you can do now. You can actually use Acronis cyber protection to protect yourself. I have to do that because that's the only way to make money at the moment. And the only money which goes to the university is my money, which is coming from Acronis. Join Kostya in building advanced materials. He will definitely talk about it himself. Join our master program. We have an amazing master program. It's really important for you to learn how to be a master in computer science if you're a physicist, and how to be a master in, say, applied physics if you are a computer scientist, perhaps. Join SIT as PhD, postdoc, permanent researcher, or just help us, right? And so this is one guy who worked in an interdisciplinary research, and one of the things he did is he got 2 Nobel Prizes. So he got 2, this is John Bardeen, he got 2 Nobel Prizes in physics. The first Nobel Prize was for transistor. We all use transistor. The second Nobel Prize for superconductivity theory. Nevertheless, we still do not use superconductivity widely. At some point, I believe we will. We use it somewhere, and it was good enough to get him a second Nobel Prize. Our chairman only have a Nobel Prize now, only 1 Nobel Prize, right? But there is still time. And that's it. Thank you very much.
Thank you, Sergei. So about 15 years ago, February or March 2004, I was still a scientist, or pretending to be one anyway, and I was a postdoctoral researcher at the University of Nottingham. So one day, my supervisor, Professor Lawrence Eves, he calls me into his office, and I get there, and he's extremely enthusiastic. He's just been to Manchester, and he tells me this story about this. He said, you can't believe what Andrei Geim and your friend Kostya are doing. They've done this experiment, and he explains me this experiment with this transistor with this thin layer of graphite. And of course, he sees that I have a puzzled look on my face, and I wasn't really getting it. He said, look, this is big. This is Nobel Prize material. I was like, okay, yeah, sure. Lawrence Eves is a good mentor because he's very enthusiastic about science, but he's sometimes a bit too enthusiastic. So I was like, yeah, okay, yeah, sure. Well, was he right that time? It took six years, I think. So I will now like to ask Kostya to come on stage and tell us his side of the story. And please help me welcome him here.
Where's the clicker? All right. Right. First of all, Fabio, thanks a lot for this story. Of course, I know that Lawrence is so enthusiastic about science, but I didn't know that he was so visionary. Of course, he is a great scientist indeed. I would like to thank Fabio and Olga for organizing this, and I'll mention later why, and also Sergei for entertaining people. So before my very boring talk, so thank you, Sergei. And so let's talk about graphene, but I would like to focus not only on graphene itself, but also what we're doing beyond graphene and where this material might lead us. Of course, I presume everybody in this audience do know about graphene. It's the thinnest possible material. It consists only of carbon atoms, and that's probably why we like it so much, because it's extremely simple, just only carbon. Carbon is a very simple element as well, but at the same time, it has a number of very interesting, very unusual properties. It's of course is the strongest possible material, is the most conductive, thermally conductive, and so on. And even having only one of those properties is enough to study this material. But what we have in graphene is a whole combination of all those properties, which really make it unique. And unfortunately, or fortunately, we're only now learning how to utilize the whole matrix of those properties together. It will really require a lot of out-of-the-box thinking. Now, because of all those properties, of course, we love it because of the science which we can do with this material, but all those properties can result in a number of very unique applications. And this is a slide I steal from Graphene Flagship, so where we try to apply graphene for sensors, energy, batteries, supercapacitors, optoelectronics, electronics, composite materials, you name it. And generally, it does work, and we really start to see lots of results coming from those unique properties. Of course, for many in this room, we would think that graphene is a very special material. So we've been playing with it for many years, lots of fun, lots of disappointments from time to time, of course, but we all think that, okay, it's really something special. And if Lawrence said that it's special, it should be true. Now, for surprisingly or not surprisingly, this material went exactly in the same pathway as many, many other materials prior to it. So if you think about carbon fibers, carbon nanotubes, there was always quite an expectation for them to be used for electronics, for many other applications, but they all ended up in tennis rackets first. So it's almost like a rule that any new material first, we test them in composites, and then the first they go into those sport goods, which is not a bad thing at all. It just I'm a big believer that the laws of physics work. It's also nice to see that the laws of economics work as well. Then, just a few years ago, we used graphene to apply it into the composite material, which was used by Richard Mille and McLaren to create world lightest, unfortunately also world most expensive watches. So if you have a spare 1 million Swiss franc, then you could get this 32-gram watch. If you haven't got 1 million, you can spend $250,000 on this sport car. It's a very interesting company, BAC Motor, just right in between of Manchester and Liverpool, very innovative. And starting this year, so at that time it was only just a test. Can we use graphene on large scale for the car manufacturing? This year, they start to use graphene in all of their cars. And the reason for that is actually not the strength and not the weight saving. It's the fact that graphene is so thermally conductive that it helps to speed up the production of those cars. Something which we as scientists would probably never thought about. And then going further, starting last year, most of the top models of the Ford cars start to use graphene under the bonnet because it helps shifting the melting temperature of most plastics up. So, and that's exactly what is required for those applications. And actually, that's probably a good moment to say, why are we celebrating this strange number 15? Because it's I don't think it's really convenient to celebrate 9 years of graphene or 8 years of graphene. It would be too early. But then past 15, so I'm just trying to replicate the thoughts of Olga and Fabio. Past 15, it will be too late, because what is going on now, really in front of our eyes, that graphene becomes a commodity, and you won't celebrate, I don't know, 100 years of stainless steel, right? So so something, it becomes so common, so mundane, so usual that you won't even think about celebrating something. And probably now is the last few years when we still can think about graphene as something special, because very soon it will become just so common a material, such a commodity, that we won't even remember that one day we all believe that graphene shouldn't exist. So, and then it went its way into, it made its way into other applications, like most of the Huawei phones now, and definitely mine, so have quite a lot of graphene inside, because graphene has the highest thermal conductivity possible, and thermal management is really one of the largest problem for modern electronics, and graphene helps solving this issue quite efficiently. But then saying all this, what we see is that graphene is still being used to replace other materials in already existing applications. As a challenge, what I would like to set a goal for myself and for other researchers is really to find completely new applications which still don't exist and which would be enabled only by graphene because of its unique properties, because of the unique combination of its properties. Let me give you just one example of what I'm thinking about, but I hope that in the future we will come with many other examples like this. So it's the adaptive contact lenses. So you take a contact lens, you put some graphene on top, you put another one on top of that, and you fill in the gap with liquid crystal. And what you can do by applying voltage between the two graphenes, you can change the focus of this contact lens, so you don't need to wear multiple glasses with you. So you can use just one contact lens and switch its optical power. And basically, no other materials can do it, because it needs to be conductive, transparent, flexible, and that's all graphene. And people are starting to think about this out-of-the-box application. So one really exciting one is the use of graphene as an impermeable membrane, because nothing can go through graphene, a part of protons. And then we can also modify this material to allow certain species to go through. And so we're lucky, so there is Rahul is here, so he produces those membranes which can allow water through, like there is no barrier at all, or we can allow some protons through, like there is no barrier, and we can use it to separate different chemicals, and probably it can be used to separate different ions as well. So we can use it for lithium extraction, for example. And then it really tells us that those applications in the unusual areas, for example, in biology. So we have a geneticist as our host. So we can. I really hope that one day we can use graphene for biological applications. So DNA translocation through a pore in graphene can help with the DNA sequencing, or drug delivery with the use of graphene, chemical sensors based on graphene are all quite realistic applications, and I'm really looking forward for those to appear on the market, maybe not in the next 2 years, but maybe 5, 10 years. Now, what I would really, as Fabio mentioned before, we had now lots of type of graphene. One of them is really high quality square meters of this material. And it's really exciting to see the huge amounts of this material, because 15 years ago, we started with really square microns of graphene. These days, we can grow square kilometers of this material. And despite that this technology is quite complex and reasonably young as well, we started to see some applications of this one-atom thick fabric. So for optoelectronics, flexible electronics, and moreover, a couple of months ago, one of the company, which is the former Cambridge Nokia, so it's called Emberian now, that they produce their first commercial chip. So they use graphene combined with quantum dots as to make extremely sensitive photodetectors for different wavelengths. So it makes it way not only in such simple applications as composites or thermal management, but it goes into the electronics as well. What I want to say here at this moment that it would be wrong to say that we have only one graphene. So we call what we call graphene is in fact a large combination of it's a family of different materials. So we have graphene platelets, we have graphene nanoribbons, quantum dots, we have CVD graphene. So the phase space which is covered by materials which we call graphene is really huge. And depending on the particular application, depending on the functionality which you want to achieve at the end, you would choose one type of graphene or another. And that's all about applications and functionality. So the choice of the material which we use should be application driven rather than anything else. So, and that's why the production methods would be different as well. So we started a long time ago with the Scotch tape technique simply by exfoliating graphite, the material which you find in the lead of your pencil. And fortunately, we still use the same method in our lab up to now, so as in many other labs across the globe. But these days we have a huge variety of different methods how to prepare graphene. Depending on the price you want to pay or the quality you want to achieve, you can use one or another type of production. And say if you want to have high quality graphene for electronics, you would use CVD method, you would use liquid phase exfoliation. Just let me maybe say a couple of words on this method. So it's you basically use any carbon-containing species to crack them on top of a surface of a hot metal, and then you can grow graphene out of the carbon, which is released by this carbon-containing gas. So when I say really that you can use pretty much anything of the carbon-containing species, I really do mean this. So I wonder how many people in the audience would recognize what's this, a part of Manchester people. So any wild guess so far? We just come on, say it. First thing what comes into your mind. Anyway, okay. This is so we needed. So it's a real experiment as usual. So we needed. I wanted to make graphene doped with ferromagnetic atoms, iron. So what you take some blood, and then you just put it on top of copper, just spread it across, so you get your carbon-containing species with some iron, and you can grow some graphene. It grows successfully. So it's I should promise that those fingers were mine, so no students were harmed during those experiments. But it just shows that you can do, you can really produce many, you can really produce graphene by many different methods. So we have liquid phase exfoliation, which is good for composites, for energy applications, and then we have really quite a large variety of smaller, less popular still, but still important methods how to produce this material. And now I think it will be a good time to switch gears. So it's probably enough to talk about the past. So let me talk about what are we doing now. And for several years, of course, we've been working with graphene in our old clean rooms. Some time ago, we established and built the National Graphene Institute in Manchester. So last year, we also built a Graphene Engineering Innovation Center. And so the research into this material is really booming in Manchester and in the UK generally. And of course, that is due not only because of the facilities, it's also because of the very enthusiastic people who work in this area. And all our students are extremely excited about all this. They're all very enthusiastic, bright eyes, bushy tails. So they're always asking me, so Kostya, you spent 60 million building the National Graphene Institute. Can we finally buy not only the lead pencils, can we buy some other pencils as well? And in principle, yes, we can, but then you can think that if you exfoliate other pencils, you would probably be coming with some other materials as well. And that's exactly, and that's really gave birth to the whole new field. So now we're not talking only about graphene research. We're actually talking about the research into the 2D materials, and even beyond that, into research of the van der Waals heterostructures. And that really, and I would like to put it more into the context of the future of the material discovery. If you think about this, somehow we as humans, we always like to give names to the times when we live by the name of the dominant material. Like you remember the Stone Age, the Bronze Age, the Iron Age. And a good question would be to ask, which age are we living in now? And probably for the first time in history, we have a choice, because you can call our time, the Silicon Age, the Digital Age, the Nuclear Age. It's good to have a choice, but then a good question is, do we actually need to make a choice? Maybe it's actually try to leave this question open and try not to focus on one material only. And it's really, and I'll show you one example why it might be beneficial indeed. So here is the periodic table of elements with the elements which we used in our integrated circuits prior to 1990. So it's silicon, boron, phosphorus for doping, aluminum for interconnects, hydrogen, oxygen for passivation. That's it. Extremely simple technology. Anyone could do it. After 1990, we started to use copper interconnects, so we had to add copper, but we also had to make the technology much more complex, because copper diffuse much more easier, and then we have to put some work function control material like tantalum, tungsten, and we also have to put some diffusion barriers, but still it's reasonably manageable technology. These days we use half of the periodic table in our computer chips. So basically what we did, we took a very old technology, starting from 1958, and we keep adapting it for new realities. And these days, it became almost unsustainable to adapt, but because of the investment, because we call our age the silicon age, we really have to stick with this. And of course, I guess you would agree with me that it doesn't work really well, because if you think how many elements is there in our body, we use many more elements in our computer chips than there are in our body. And of course, we function, as Sergei said, as the best computers in the universe, who function much, much better than our computer chips. So, and generally that's the case, that our world really relies on only few materials, and we would like to escape this slavery of those few materials. We would like to use many more materials, and we try to do it by combining different materials and the properties of different materials together. We call them composites or heterostructures. Those examples do exist, but there are still few and far between. So ideally what you want is for any new application to be able to design a new material from scratch by atom, or at least layer by layer engineering, and then you can encode different properties and different functionalities into every layer. And because we have now this, and we start to do it with the custom manufacturing already, you can design something, send it away, and you receive back your design piece. We start to do it with chemicals as well. You can design a short DNA, just simply type ATG in your email, send it away. A few days later, you receive your short DNA. Can we expand this into all the materials in general? Can we design new materials for any new applications? And before I give you a solution, let me tell you a small story. So as I said, last year we opened the Graphene Engineering Innovation Center. A few years ago, we opened the National Graphene Institute. Nancy is here, George Osborne is here. So that's President Xi Jinping. So that's how it looks now. And that's how it looked about 7 years ago when we started to do the archaeological survey and in Manchester, where we were quite happy to discover rows of terrace houses from the beginning of Industrial Revolution in Manchester, 1790, 1820, but also the remains of a fairly large building over here, which has been identified as an Albert Club house in Manchester. The Albert Club house was a club for German expats in Manchester in the beginning of Industrial Revolution, and we probably won't know much about it, won't remember much about it, but this gentleman was a member of this club. And this is Engels, and of course, once we learned about all the stories, so we were quite lucky with our archaeologists, so we really uncovered all this story. My knee-jerk reaction was we should call this new building the Engels building. It's a tradition that every single building on the university campus should be named after a famous Mancunian. So physics is a Schuster building, math is Alan Turing building. So the idea was that should we call the National Graphene Institute the Engels building? So Nancy was reasonably neutral when we passed this message to George Osborne, because he was heavily overseeing all the construction. He just tapped me on the shoulder, said, Kostya, I give you research I give you money to do research, not to explore your communist past. And but same as the Communist Manifesto hasn't been written by Engels alone, it would be stupid to call to study graphene in the National Graphene Institute. So we really hope that we're going to study many other materials there, not only graphene. And so imagine what is going on in the NGI now, that we come to work and we have those all those two-dimensional crystals available to us. It's like a library of those materials. It's like sheets of papers with some stories written in it. But now what we can do, we can make the next step. We can take those materials and start putting them together, one on top of each other, back into a three-dimensional stack, and then we can create an artificial material which Mother Nature never intended to create, but we can design it and create in our labs. And it is happening already now, and we create a lot of new materials, new devices based on this technology. It's called the Van der Waals heterostructures. So we create new types of transistors, LEDs, photodetectors, lasers, and so on. And it works quite well, and it really turned out to be a very extremely versatile technology, and it produced a lot of new physics, but also a lot of new applications. So here is probably one of our most advanced heterostructures. So if you apply voltage, you get light out of it. So it's an LED, and we're working on making lasers now, and it's really something which is of high demand, because we have a huge variety of those two-dimensional crystals. It's really several dozens of that. Because we have many of those crystals, we can cover, for example, in terms of the light emission, we can cover a huge, very broad range of the optical spectrum. Probably for what is most important for technology are those molybdenum ditelluride, because it sits right in the telecom range, and that really solves all those issues which Serguei was mentioning about how to make our internet faster and how to make our internet signal processing much more efficient. So we start to work on the quantum dots based on those materials, and those quantum dots you can incorporate into LED devices, and you can emit single photons on demand. And again, this is extremely important for quantum telecommunications. So those quantum dots are extremely bright, and we can produce them on demand at any spot, and we can make them any color we want. So that already pushed for new generation of the telecom devices. As I said, graphene combined with silicon photonics is an extremely versatile combination, because we can nothing else can give you 50 gigahertz modulation of the optical signal. At the same time, we have lots of work done in the graphene flagship, where we combine silicon photonics and graphene, and already produced optical modulators which are sufficient for 5G, maybe even 6G technology. With the one of the big issue for the telecommunications is the lack of the light sources which work in the telecom range. We have to do either wafer bonding or the fiber bonding. With the 2D materials and with the heterostructures based on 2D materials, we can simply grow those conformally on top of the silicon photonics chip, and we have our light sources and we have our light detectors. So now we have really materials with predetermined properties, and we have materials with the properties which we can design on demand. But what we want to make a step further, and we want to make materials not only with properties but with functionalities. And functionalities are the properties which exist in time, right? So what the current paradigm in terms of the material design is that we take our material, we have certain properties which are inside of the material, and then the functionalities come on top when we create a structure out of it, like we create a transistor or the whole integrated circuit. For example, the biological systems like our body works in a completely different manner. So we have functionalities built pretty much on every single level, like there are certain functionalities in the membranes, on the cellular level, on the organ level, on the whole human body. So this hierarchical structure of the distributed functionalities is extremely important for the efficient operation of our body. And that's exactly what we're trying to develop now, based on the 2D materials, but also combined with some other materials as well. So we're trying to create materials not only with the predetermined properties, but with the predetermined functionalities. And we have some ideas how to do it. So we're really trying to create materials out of equilibrium. So those which don't have just one or two stable points, but which would be described by a whole landscape of the potential minima, and then you can navigate through this landscape simply by changing the external conditions. So that's in a nutshell where all this technology moves and where the material design moves. Now I should say that probably those heterostructures which I showed you before and these new functional materials is still something for the future, and we're still working on many other, but already now we can try to produce those heterostructures based on simpler technology. So it takes weeks maybe for our students to produce one material, one stack based on, I don't know, 20 different materials. But what we can do, we can produce inks of those materials, and we can put them into an inkjet printer, and we can start printing, any complex heterostructures based on those 2D crystals. And that's quite a realistic technology, and we start to use it already for certain applications. So there is a spin out from the University of Manchester where we already started to use graphene ink to produce very simple electronic circuits based on this material. So we call them. So one of the product is the RFID antenna, is something which is extremely important for Internet of Things applications. And what really makes me happy is that we start to print not only with graphene, but for HF antenna, we start to print with boron nitride ink as well. So other 2D materials start to go into those applications on the par with the graphene itself. So these days it's a fully functional production. So it's really good. It's really nice to see that not only graphene but other 2D material start to move into the applications, and and we really hope that within a couple of years we can produce active RFID antenna, and we start to use them for the real Internet of Things applications. So let me probably stop here and just put a few remarks for you here. That we had really fantastic 15 years with graphene, lots of science done, what is amazing that within a short period of time, this material moved from science, and still exciting science, to almost full scale of application, up to a point that maybe within a few years it will be too late to celebrate this material. What we're focusing on now is the use of many other 2D crystals in applications, but also in our scientific experiments. And probably the future of the material science is in designer material, is in designer functional material, which will hopefully change the whole paradigm of the material science and the paradigm of our modern technology as well. Thank you so much for your attention. Thank you.
Okay, you can stay there. You're happy to take some questions?
Sure, absolutely.
Okay. The floor is open to questions, so if anybody has any question, we have some microphone that can move around the room. Questions, anyone? Am I going to start? So you didn't make much mentions of magnetic two-dimensional materials.
All right, so I have a full lecture, a full seminar, but
Can you tell us something about it? Or
so what is, of course, why 2D materials are generally interesting is because of its topological properties. The topology in 2D is, of course, very different than in 3D. Like you cannot have knots in two-dimensional in 2D, and that changes a lot of things. And in particular, it was always exciting to know if we can get two-dimensional superconductivity and if we can get two-dimensional ferromagnetism, because they would behave quite differently. The quantum criticalities would work very differently for those quantum phenomena in 2 dimensions. And some time ago, both superconductivity in 2D and later ferromagnetism in 2D were discovered. We get quite a large family of 2-dimensional ferromagnets now, and it's really exciting direction of research, because you can probe those materials not only magnetically but also with the electric field, because you can change the coupling constants, you can change the strength of the interaction with electric field, with doping, with magnetic field. And so these days we probably have a good more than a dozen of those 2-dimensional magnets. Some of them are metallic, some of them are insulating semiconductors. We gradually learn how to work with them. So we study them by optics, but also by transport. Unfortunately, it's those materials are only magnetic below at quite low temperatures, so they're not ready for applications. And of course, the area of magnetism is dominated by large corporations who are always eager to use it for various kinds of memory. We're not there yet, but there are some ideas how to make them magnetic at room temperature as well. So it's probably one of the most active area of research in terms of 2D materials at the moment.
Okay. Any question there?
So when you said that you could choose which particles could go through a graphene filter, how long will it take for the graphene filter to break down after many uses, and even would it break down?
Well, so it's, I mean, I'm not really working much in this area myself. I can redirect this question to the expert, but and I'm sure that Rahul will be able to answer those questions after the lecture. But generally, I would say for some applications, graphene filters, I would call them graphene membranes. They work equally good as the current filters. But for example, applications like water desalination is so advanced and so developed these days that I don't think graphene would be able to get into those applications. At the same time, ion extraction, I think, is a very, very realistic area where it can be used, or extraction of the radioactive elements for decontamination. So those areas are in principle ready to use graphene right now. So it's more a question of technology rather than science.
Okay. There's a question over there.
Hi. We see a lot of students in the room. Some of them might consider also starting a business. Now, if they wanted to start a business in the area of graphene and the other condition, they wanted to get as rich as quickly as possible, which application would you suggest they choose?
I mean, it's obvious, right? So what you do, you just follow me, where you just follow my investment portfolio and just do the same. I mean, if I knew, would I tell you? But you see, it's I think. So what we've seen over the last maybe 5-6 years, there were a lot of companies focusing on graphene production, which I think is wrong, because you cannot produce one type of graphene and then hope that it's going to be used for many different applications. So you would really, so my advice would be to start not with the graphene production, but with the final product. And then if graphene is really good for it, so then you use graphene. If something else is good for it, so then you just use another material. I'm not an advocate of graphene at all. So I work with it because it's really exciting. It's simple. You can get it high quality, but at the same time, I would say I'm reasonably promiscuous. So I would go in bed with any other two-dimensional material which shows nice physics. So I'm switching now to 2D materials, 2D magnetic materials. So it's really wrong to focus on one material and then hope that it will give you good applications. So it's like in my lecture, I was trying to deliver this idea that it's wrong to focus on the properties. You need to focus on functionalities, and it's because functionality is at the end of the day is what you want. So we've seen so many companies which focus on graphene production grow and fail and collapse at the end, that I would definitely recommend those students to come with idea how to solve the burning issues of humanity, of humankind, of technology. And then if graphene is good for it, you just use it. If not, there are many other materials which to use.
Any other question?
Hello. So I would like to ask about graphene and printed antenna. So a slide that you showed, an antenna printed on a paper, I think. Do you see any improvement in the electrical performance using graphene, other than using the conventional copper?
Right. Realistically, those antenna, it's quite a simple piece, right? It only depends on the conductivity of the metal, and so it doesn't matter which material to use as long as it gives you the same conductivity. So in terms of the performance, it's pretty much the same. So you use aluminum, you use copper, or you use graphene antenna, they operate exactly the same. So the reading range would be up to 10, maybe 12 meters, same, but basically exactly the same. It's limited by the conductivity and by the design. What is different though is the production method, because copper and aluminum technologies are the subtractive technologies, so you have to etch those materials which produce waste and which are not environmentally friendly. The printing is the additive process, so it doesn't produce waste at all. Also, you have an advantage that you can print on paper, not on plastic. So, and of course, plastic is now forbidden in Europe. And generally, the production factory the production line is much cheaper for the printing technology rather than for the etching technology. So, if you want to establish a factory on the production of RFID antenna, which I would deeply not recommend, you would be much better with the printing technology rather than with the subtractive technology.
Olga, I think, has a question.
Yeah, I have a Nature Nano question here. So you already mentioned, I think Fabio mentioned 2D magnetism, and then we also mentioned unconventional superconductivity and bilayer graphene as two big discoveries in the last 2 years. If you could pick one result, one paper maybe published this year, what would it be?
Right.
Maybe not of the same magnitude, of course, but something that you find particularly important.
I think, I hope that we don't need to limit ourselves to graphene, but I quite like the progress in the area of the two-dimensional membranes and on the proton membranes, which is going on now, because I think it has a lot of potential for applications, and not only in batteries but also in functional membranes for biological applications. So I think that's if we leave aside magnetism and superconductivity, so those are the next big things.
Any more questions? If not, I'd like to thank Professor Novoselov again.
Thank you.
And I'd like to thank also... well, I'd like to thank you all for coming. Thanks to all the speakers, Magdalena and Serguei. And I thank you all for coming here and for enjoying this evening. And I hope you will stay for us a little bit longer. We have a little reception at the back. Thank you very much.